Right, welcome back to our subject Aircraft Propulsion Systems. So we are already in week number or lecture number 13. So for today we shall continue on the chapter 7, shaft engines, turboprop, turboshaft, as well as prop fan. As we all aware that we have already looked into the topic on turboprop. We shall continue today to further look into the aspect of turboshaft as well as the prop fan. In terms of the overview for our lecture today, the plan is that for the first hour we'll shall look into the subtopic of 7.3 turboshaft engine, and then we are going to have a short break in between 7.3 and 7.4. Right after the break, we will continue on the prop fan engine subtopic. In terms of the turboshaft engine, we will go through the following section. First, of course, we are going to look into the overview, and then to see some examples for turboshaft manufacturers as well as turboshaft engines. And then we will continue with the thermodynamic analysis of turboshaft engines and end it up for the power generated by turboshaft engines. Right. A turboshaft engine, similar to what we had gone through for the turboprop engine. Okay, so we will now look into what are the elements of turboshaft engine. It's basically a form of a gas turbine, right? It is included in the family of gas turbine engine, which is optimized to produce shaft power, right, rather than jet thrust. Okay, so it's compared to turboprop, it is producing jet thrust, but this turboshaft is basically want to focus on producing the shaft power. Generally, a turboshaft engine is made of two major part assemblies. Of course, the gas generator, right? And then the second part of the assembly is the power section. Okay, those are the two things that we are going to look into in our lecture today. The gas generator consists of one or more compressors, like the turbojet. It can have one compressor or more compressors. Similarly, with the turbines, you can have more or one set of turbine section. Of course, in terms of combustion chamber, we have the set of combustion chamber over there. And for the power section, the power section consists of the additional turbine apart from the turbine that included in the gas generator. We have additional turbine, a gear reduction system, and the shaft output. So this is the second major part assembly for the turboshaft engine. Compared to normal jet engine, you have only the gas generator, because gas generator will produce the thrust. But for the turboshaft engine, they have another section, a very important section, which is the power section. And this will in turn producing shaft power. The gas generator creates the hot expanding gases to drive the power section. So basically, the power section does not produce its own energy to turn the turbine or to turn to produce the shaft power. So it get the energy from the gas generator. So depending on the design, the engine accessories may be driven either by the gas generator itself, a gas generator section, or by the power section, right? So in most designs, the gas generator and the power section are mechanically separated so that it can rotate at different speeds. And this is a common arrangement for the design of the turboshaft. So turboshaft engine. So gas generator and then the power section itself probably having mechanically separated segment or gears so that they can rotate at different speeds to optimize its function. The turboshaft engines similar to turboprop, except that the hot gases are expanded to a low pressure in the turbine compared to the turboprop because it want to provide greater shaft power. That is the main purpose of the turboshaft engine, to provide greater shaft power with little exhaust velocity. Compared to the turboprop, they also provide shaft power but having exhaust velocity that produces also significant to the thrust generated by the engine. So they differ primarily in the function of the turbine, because the turbine is operated at low pressure. Instead of driving a propeller like turboprops, the turbine is then connected to a transmission system. Normally it is to drive helicopter rotors. So those helicopter engines having common turboshaft arrangement. Other turboshaft engines that will be identified as industrial gas turbine are used for land and sea application. It can also be used for power generation for land as well as sea applications. Examples for land applications, we have electrical generators, compressors, pumps, auxiliary power units, pumping units for natural gas in cross-country pipelines. You can also have it in tanks, race cars, where power turbine will drive the transmission system. So basically, once all of you completed your Bachelor of Aerospace Engineering, right? So not necessarily you are going to go into the aerospace industry. You can also diversify going to other relevant sectors such as power generation. You can also go for automotive. You can also go for other application. For example, like the one that we are going to look underneath here, examples for marine applications such as naval vessels to power the turbine for the ships, cargo ships, hydrofoils, hovercraft, and other vessels where power turbine drives marine screw. All right, so to produce propulsive thrust. All right, so that's why it is important for aerospace engineers to be able to understand the basic principles of other application for turboshaft engines. Many aero engine manufacturers have already produced two versions from an engine, one as turboprop and the other one as turboshaft engine. Example, PT6B and PW206, which is produced by Pratt & Whitney of Canada, as well as Allied Signal LTS101, 600A3, and Ellison 250C30M. And this is an example of other type of engine that are produced by manufacturers around the world. An unusual example of the turboshaft principle is provided by Pratt & Whitney, which is the F135 PW600 engines for the short takeoff and vertical landing F-35B. Okay, so the stealth fighter F-35 are using turboshaft engine. So turboshaft engine by Pratt & Whitney. In the conventional mode, it operates as a turbofan. Okay, but when powering the lift fan for the vertical takeoff, it switches partially to turboshaft mode to send power forward through a shaft like a turboprop, and partially to the turbojet mode to continue to send thrust to the rear nozzle, right? So it is a quite complex type of engine, because it can have a short takeoff and vertical, and also it have a high powered for forward movement. The turboshaft power is measured normally in shaft horsepower, SHP, or normally denoted by kilowatts, kW. All right. Now we want to go into the examples for turboshaft manufacturers as well as the turboshaft engines. In terms of the examples, we will look into different manufacturers, and we will also look into what are the type of engine being produced by the respective companies. The first one is Pratt & Whitney of Canada, known as PwC. Built a great family of its popular turboshaft engine, as being highlighted earlier, PT6 as well as PT6A. It already powers numerous helicopters, including the Sikorsky S-58T. Right, you may want to try to Google the picture of the engine as well as the helicopters that are being mentioned here. And then we also have General Electric that built several turboshaft engines, including the CT-58, which powering Sikorsky's S-61 as well as S-62 type of helicopters, and the Boeing vertical takeoff or VTOL CH-47 helicopters, and also the famous T-700 or CT-7 turboshaft engines, which power the Bell AH-1W Super Cobra. Okay, so those are the first two, Pratt & Whitney as well as the General Electric company. Moving into the third company, which is the Allison Engine Company, which already started to build turboshaft engine way back in 1960s. They produced Allison Model 250, and since Rolls-Royce also already acquired Allison, because it is bought over by Rolls-Royce in 1995. The engine itself, the engine model itself, Allison engine, already known as the Rolls-Royce M250. Okay, and it is also designated as T63 or T703 for the US military designations. The type of model, also Allison Company also powered many helicopters, including Agusta A109A, the Bell 206B, L 206LT, the Bell 407, Bell 230, and Bell 430 type of helicopters, and including the Boeing AH-6 as well. So you may want to look into what are the series of Bell helicopters over here, and the Agusta type of aircraft as well as the Boeing helicopters. The fourth type of company that we would like to look into is Lycoming Company, that built the Lycoming T55 L7C, powering the Boeing VTOL Chinook, the transport helicopter, CH-47, as well as the Bell 309 and Piper PA-48 Enforcer. Right? There are other various companies also involved in the turboshaft manufacturer, such as Turbomeca, that responsible to build the Aries 2K1, which powers the Eurocopter EC-120 Colibri and used in tourism over New York City and other cities over the world. Rolls-Royce also built numerous turboshaft engines, such as the GEM, powering Augusta Westland Lynx helicopter, right? A transport helicopter that being used by oil and gas or business transporter, as well as the AE1107C Liberty turboshaft that powers the Bell Boeing V-22 Osprey. This the helicopter that can have a rotation in terms of vertical takeoff, as well as the it can also rotate to have a forward speed. The Rolls-Royce Turbomeca RTM322 turboshaft engine powered the Augusta Westland Apache and Augusta Westland AW101, as well as the NH90. All right. So next one, going into the Russian Federation. Okay, we have the company Soloviev Design Bureau. Right, it is a government-owned company which built one of the earliest Russian turboshaft engine, namely the D25V in 1957, having 4,780 kilowatt, around 5,500 horsepower, that powered the Mi-6, Mi-10, as well as the Mi-12 helicopters. With regard to the Ukraine, the Ukrainian 3-spool turboshaft engine D136 Series 1 powers the Mi-26 transport helicopters that are basically the largest in the world, and other famous Ukrainian turboshaft engine including TB3-117BMA, which uses to power the KA helicopters, and the TB3-117BM powering the Mi-17 and Mi-8 AMT helicopters. So there are so many good examples of turboshaft manufacturer as well as the turboshaft engines. Let us look into one example here. Okay, I'm going to show you figure 715, which illustrates a helicopter during hovering close to the ground. A control volume with inlet and outlet dimensions is also shown in the figure, and the total mass of the helicopter is given as 2,000 kilogram. The exit static pressure, P static, is atmospheric, assuming the flow is a one-dimensional, steady and incompressible. We want to calculate the exit velocity of the air, V2, and the power of the turboshaft engine. Right. So I actually rotate the figure. Rotate the figure is actually vertical. Everything is vertical because it is a helicopter. Okay. The diameter of the intake of air is 3.3 meter. Okay. We have velocity 1, pressure 1 coming into the propeller blade, the blades for the helicopters, right? And it flows through the we want to find what is V2 over there, okay? And this is basically a schematic of the control volume from section 1 to section 2, right? We want to find what is the exit velocity at V2 over here, okay? In terms of the solution, now we know the control volume enclosing the helicopter, states 1 and 2, identifying the upstream and downstream of the rotor is shown in figure 715 just now, and both ends have a diameter of 3.3 meter. And both ends mean that we at 1 it is 3.3, at 2 station it is 3.3 meter as well. While the helicopter body at the control outlet volume is a circular diameter of 3.0 meter. So this is, imagine the body of the helicopter having a diameter of 3 meter. Using continuity equation, okay, we assume that the mass flow rate at station 1 and is equal to the mass flow rate of air at station 2, which is also denoted as m dot. So continuity equation, we look into the density, the velocity, and the area, which is equal at state 1 as well as state number 2. For any incompressible flow, then we can know that the velocity at 1 equal to velocity at 2 times the ratio of the area at 2 over ratio at 1. Applying the momentum equation, okay, applying momentum equation as follows, right? So you can then have, for steady flow, you will get the expression of the forces in terms of the pressure at station 1, P1 GA1 and minus P2 GA2 plus mg, the weight of the aircraft already given, okay, and equal to the mass flow rate time the velocity difference V2 minus V1, right? So P1G is basically the gauge pressures at station 1 and station 2. Moreover, from the Bernoulli's equation, we can then express in terms of the atmospheric pressure plus the dynamic pressure. Okay, basically the in terms of the kinetic energy there. Okay, at station 1 as well as station number 2. With the V infinity equal to 0, we then equate the equation basically P1G, which is equal to the dynamic pressure at station 1. From the equation A, okay, we can then express it as follows. We rearrange it with P2G equal to 0. Then from equation A and B, we will then get the following. We can follow through the equation to get a velocity equal to the square root of the weight mg over the density times the area at 2 times this element of the ratio of areas over there. So since in terms of the area for A1, we already know A to get pi over 4, 3.2 times 3.3 squared, you get the area 1 to be 1.484, and calculating the density of air, okay, the density of air P over RT, you get 1.22 kilogram per cubic meter. And finally, you get the velocity at exit of the control volume at state 2 to be 108.93 meter per second. Okay, so that is quite simple to apply the equation in terms of the helicopters application. From equation A, moving into the next part of the question, right? So you have the velocity V1 to become 18.9 meter per second. Finally, applying energy equation for the same control volume, okay, Q dot plus W dot, and the work in terms of this energy equation. For adiabatic flow, there's no heat element and no heat transfer, whereby Q dot equal to 0, and the steady condition is as follows, and you get the only the element of the work, okay, the work flow that is equal to the mass flow time the velocity difference squared over 2. Okay, since we know that m dot equal to density times velocity times the area, you know the value of the density, the value of the velocity, and then the area involved, you get m dot, the mass flow rate, flowing through the rotor, okay, upstream and downstream. It is equal to 197.22 kilogram per second, right? The workflow for the system is then calculated for 1134.8 831 kilowatt. Okay, that is basically the power of the turboshaft engine, W dot. Okay, for that is what already being obtained down here. Okay, we will continue to the next segment, which is 7.3.3, the thermodynamic analysis of the turboshaft engine. A turboshaft engine also has two configurations. Either the load is driven by the gas generator shaft, or the same gas generator shaft, or driven by the free power turbine, and it's going to be shown in figure 716 as well as 717 respectively. So the first configuration, where the load is driven by the gas generator shaft, resembles a single spool engine, right? Whereby the second arrangement, the load is driven by free power turbine, is known as the two-spool engine. Okay, the load may also be installed either toward the cold or the hot sections. So this is the single spool turbo shaft, where the load itself it is driven from the single shaft, where it is connecting the compressor with the turbine directly to the load that you want to apply. Okay, and this is for the two spool arrangement, where the power shaft, the load itself, it is driven by the free power turbine. And the free power turbine, it meaning that it is not mechanically connected to the main shaft, which is the compressor turbine, the turbine, as well as the compressor, because it is this is connected into one type of spool. This is a single spool, one spool, then the other one is the two spool. So this is a two spool turboshaft engine driven by free power turbine. Now we want to look into the thermodynamic cycles. We will also look into the temperature entropy diagram for both the single and double spool type of engine, which is shown in figure 718 and 719. It is noted that the hot gases expand in the gas turbine, which is the single spool, or a free turbine double spool, to nearly the ambient pressure. Okay, so the hot gases will expand nearly to the ambient pressure for both situation, for single spool and the double spool. So this will provide a greater shaft power, okay, not producing velocity, because little exhaust velocity will be produced in both arrangements. So this is the TS diagram for single spool turbo shaft, where you have the normal TS diagram. We can see here the at station 1, okay, PA equal to P02, okay, and the pressure build up with temperature, okay, at station 3, moving into station 4 right after the combustion chamber, okay, where the temperature is at the highest, okay, similarly with the entropy, and before it move into the pressure at the exit, okay, at P5, okay, where P5, as we know that the pressure is equal, this is a equal pressure line, PA equal to PO2 and P5. Looking into the TS diagram for double spool, it looks similar, but you have more stations. We then have P6 over there, right, at the exit, instead of the P5 just now, where the free power turbine is at P05. The turbine that is connected to the compressor is P0. T04. Alright, so the temperature already dropped a little bit from turbine that is connected to the compressor compared to the free power turbine that is having the second spool. Right? Right. Let us look into the power generated by turboshaft for both situations. First, we want to look into the single spool turboshaft, and then later we will look into the double spool turboshaft. From figure 718 at the TS diagram just now, as well as the schematic for the single spool turboshaft, the analysis of the diffuser, the compressor and combustion chamber is typical to that a turboprop engine. It's quite similar, right? So let us look into the turbine section, where the turbine drive both the compressor and the load. It is interconnected, and assuming full expansion in turbine to the ambient pressure. Okay, and then the specific power delivered to the output shaft, W shaft, is expressed as follows. We have the component of the efficiency of the mechanical efficiency of the turbine, mechanical efficiency of the compressor at the same time, and the work by the turbine and the work by the compressor. Okay. From figure 718, right? Just pick up again figure 718 so that we do not have to go back and forth. The analysis of a diffuser, compressor and combustion chamber is typical to that a turboprop engine. And the turbine that drive both the compressor as well as the load, we already seen this, where the F is the fuel to air ratio and B is the bleed ratio. Okay. This shaft which drive the load here, basically the rotor of the helicopter blades, experiences some mechanical loss. And of course, it's not 100% efficient, right? There are mechanical losses due to friction in the gearbox as well as the bearing, and normally the load power equal to the mechanical efficiency time the shaft power. All right, then the load power is then P load equal to M dot A W load, and the work times the mass flow of the that goes into the rotor blades. Meanwhile, for the double spool turboshaft, let us look into the double spool turboshaft arrangement. The diffuser, the compressor, and the combustion chamber also will be treated in the turboprop section, similar, but the only difference is the free power turbine. Okay, so let us look into the gas generator first. Gas generator turbine, the turbine which provides sufficient energy to drive the compressor. Thus, the outlet temperature is obtained from the energy balance between the compressor and the turbine. And this is quite similar earlier. So you have TO5 equal T04. Using equation 7.20, right? You will then get T05 value. And with regard to the pressure, you can then get P05 to be equivalent to this expression, where we have the efficiency of the turbine is included over there. Now the section of the free power turbine. Okay, the gases are assumed to have a complete expansion to ambient pressure. So thus the power delivered to the load, power to the load equal to this expression or equation 722, right? So, and we have the component of the fuel to air ratio, the bleed, the mechanical efficiency. We also have the specific heat capacity at constant pressure for the free turbine. FT is free turbine, and temperature at 0.5, basically temperature at the free turbine section, and the pressure ratio between the ambient and the P05, basically the the free turbine section at the state at P05. Okay, before we end, we want to go through one example, quick example, 7.5. Okay, this figure 720, we are going to be shown figure 720, which illustrates a Bell 206 helicopter, which is powered by Ellison 250 C20B turboshaft engine. So this particular engine, the Ellison 250 C20B, is basically a two-spool turboshaft, right? Where the gas generator is composed of a compressor driven by a gas turbine, while the power or free turbine drive the helicopter rotor. Okay, so you will be using the earlier explanation, the theory that we just looked into the previous slides to be applied in this situation. So this is the Bell 206 helicopter. This is a Los Angeles Police Department helicopter, right? So it is basically using double spool turboshaft engine. Parameters given over here, the air mass flow rate, 1 kilogram per second, compressor pressure ratio, 6.2, which is the pi over there, turbine inlet temperature, 1258 Kelvin, fuel heating value, Q equal to 43 megajoule per kilogram, pressure drop in the combustion chamber assumed to be 4%, and the efficiencies for the relevant components for the turboshaft engine. The compressor efficiency is 0.8, the bleed efficiency 0.96, the gas turbine efficiency equal to the power turbine efficiency 0.82, and the mechanical efficiency 0.98. So you want to assume it is a ground operation. Okay, calculate the power delivered to the helicopter rotor, basically power delivered to the free power turbine, and then calculate the SFC, specific fuel consumption. Right. In terms of the solution, figure 20, 720 illustrate the layout of the two-spool turboshaft and the states, relevant states, and 719 illustrate the TS diagram. For ground operation, intake, basically state A to state 2, the outlet condition T02 equal to the T ambient, which is 288 Kelvin. The pressure is at 02 equal to pressure at ambient because it's at ground. It's still at the ground level. It is 101 kilopascal. And for state 2 and 3, we're looking into the compressor, the outlet condition P03 equal to the compression ratio, compressor ratio, pi C times the pressure at the state 2, you get 6.2 times 101. You already get the value of the pressure at the compressor state, 622.2 kilopascal. Then using the expression for the temperature, okay, you put all the numbers there. We have the efficiency of the compressor. Okay, you will then obtain the temperature at the compressor at state T03 to be 535 Kelvin. Moving into the combustion chamber, right? So you look into the P04. You want to find the P04. You already know that there is a pressure drop at the combustion chamber. Then you have to take into the account. So basically, time the P03. So that is the value at the exit of the combustion chamber, 601 kilopascal. And the fuel to air ratio, F, okay, is obtained here. from the value, various parameters over there, and you get 0.0228 fuel to air ratio. In terms of the gas turbine states, the state that 4 and 5, you then obtain the T05 to become 1042 Kelvin. Okay, 1042 Kelvin compared to the earlier temperature before at the compressor 535, right? And now at the inlet of the turbine section is already 1042 Kelvin. And for the pressure at the gas turbine, the turbine that at the gas generator, you get a value of the P05 to be 235.126 kilopascal. Moving into the power turbine, and the free power turbine, state 5 to 6, right? We know that P6 equal to ambient, atmospheric. We assume it is fully expanded, okay? It is equivalent to the atmospheric pressure, 101 kilopascal. Then you can then obtain the value of the T6, which is still very high, okay? But lower than the temperature at the gas turbine just now, turbine that gas generator. Now T6 is 897.3 Kelvin, and finally you get the work for the free turbine to become 191 kilojoule per kilogram. Finally, with regard to the power delivered to the rotor, power of rotor, you have the element of mechanical efficiency over there. You put all the numbers in, you get the power delivered to the rotor or the helicopter blades is equal to 187.2 kilowatt. Meanwhile, the specific fuel consumption, since you already calculated the fuel air ratio, you have the power to the rotor and the mass flow rate 1 kilogram per second, then you will obtain the value of specific fuel consumption for this Bell helicopter of 0.438 kilogram per kilowatt hour. All right, so quite straightforward, but there are a few equations that you may need to pay attention in order for you to apply the situation for this double spool turboshaft example. All right, so I think that will be a good time for us to stop for a break, and we shall have a break of 10 to 15 minutes and to continue the remaining subtopic for turboshaft, turboprop and prop fan engine. We will look into prop fan engine right after the break. Okay, thank you very much. I'll see you in 10 to 15 minute times.